I'm going to be teaching you basically how computers work, more or less. How computers, you know, how they just always deal in a bunch of ones and zeros, and what the heck does that mean? I'm going to teach you today how computers store digital information and transfer it and stuff. And it's going to be really cool. So, I'm going to start off with this video because it's super relevant on like 4 different levels. So,
Like 4 different.
Base 10. When we count, we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we get to 10 and we take the 1 again and put a 0 after it. There's no reason why that has to happen at 10. It could happen at 12. It could happen at 18. It could happen at 3. It could happen at 5. Binary is when it happens just after the 0 and the 1. Base 10 isn't special at all. It's actually probably more annoying than some other systems we could use. Base 12 might be better. We in fact use base 12 a lot, but we talk about dozens. Probably we use base 10 just because we have 10 fingers. That's the reason. Bugs are gross. The culinary.
So, pretty much the question is, like, how are we watching this video? How did he shoot that video at his home and then upload it to the internet where I could access it and now show it to you guys? Like, how does this transfer of information happen in just a bunch of ones and zeros? Digital information storage and transmission is the exact same thing as like regular information storage and transmission. Like, I have an idea in my head right now. If I want to get that information from my head into your guys' head, how do I transfer that information?
You speak it.
I speak it, exactly. Do you guys realize how crazy awesome that is? Like, we invented language. Pretty much, I want to tell you guys right now how old I am. So I have this idea in my head. I'm trying to get into your guys' head. I need some markers. So we invented these sounds. Like, words are just random sounds. But if I want to tell you how old I am, I make the sound I. And you guys know that now I am talking about myself. And then I make the sound am. And that tells you guys that I'm talking about my state of being. And then I say 26, and that means something to you as like a quantity. Like, the fact that I can just make noises and you guys understand the idea that's in my head is craziness. But then it got even crazier long time ago, when we invented written language. We associated that sound I with this symbol here. That's craziness. Like, you guys can see a symbol that I wrote down or that someone else wrote down like thousands of years ago and know that idea that they had in their head way back then. Craziness. And then am, okay, well that's actually 2 different sounds put together, right? There's an a and an So when we got to written language, we're like, okay, we're going to have to give each of those sounds a symbol unto itself. So we'll give the a sound this symbol, and the sound this symbol, and now you guys can write the word am. And then we invented numbers. That means something to you guys. That is craziness. But how would I go about doing this if all I could use were ones and zeros? Like, humans are crazy, crazy smart. We can recognize so many different symbols. There's the 26 letters of the alphabet. We can recognize both the uppercase and the lowercase, not to mention all the different fonts and cursive and whatnot. We can recognize all 10 different digits, and then we figured out how to use more than 10 digits by sticking them together in this awesome system. Like, and then we can recognize all the different symbols on the keyboard. There's the @ symbol, there's the pound symbol, there's the dollar symbol. There are thousands of symbols that you guys can recognize just like that. But compared to us, computers are super stupid. They can only recognize 2 different symbols, or 2 different states, basically. There's on and there's off. We call that 1 and 0 when we're talking about computers. So, how, if I wanted to convey this idea in ones and zeros, would I go about doing it? Any ideas?
It's a 0 until the letter I in the alphabet, and then it's a 1, and you go back to 0.
That is a very interesting idea, and it would work, but it would not be nearly as efficient as the system that they ended up figuring out. So, the first idea that occurred to me, that is a great idea though. The first idea that occurred to me is, okay, well, we pretty much need to associate each of these symbols with a string of ones and zeros. So, now when we get to G, we're going to have to triple up, and this is just becoming a mess, because, like, If you see 1, 0, does that mean C or does that mean AB? Like,
What means space? Or
yeah,
you're
well,
cutting it off.
we are gonna definitely need a string of numbers that means space. But pretty much, wouldn't it be a whole lot easier if rather than just 1s and 0s, we could associate each of those symbols with a number, right? So, all right, we'll say A is 1, B is 2, C is 3, D is 4, and so on. Like, that would make things so much simpler, but then we'd need to be able to count in binary. Well, we can count in binary. Binary is just a number system, just like decimal. Like he said, decimal is completely arbitrary. There's no reason we have to start over and start using a second number when we get to 10. It could have happened at 12, it could have happened at 5, it can happen at 2. So the way number systems work is pretty much this. If I write the number, you guys are familiar with decimal, that's probably all you guys know. So if I write the numbers 3, 6, 5, you guys think of that as 365. What you're actually doing is going back to like elementary school for a second. This is the ones place, right? This is the tens place, and this is hundreds place. So what you're actually doing, even though you're not really conscious of it, is doing 3 times 100 plus 6 times 10 plus 5 times 1 is 300 plus 60 plus 5 is 365. You can do the exact same thing in binary, except now the first place is going to be the ones place. What's the second place going to be? It's not going to be tens.
Zeros?
Twos, very good. Twos place. I want to take a guess at what the third one's going to be?
3.
1, 2.
See, what's actually happening here is it's better not to think of this as 1, 10, 100,000. It's better to think of this as 10 to the 0, 10 to the 1, 10 to the 2,
So 4.
10 to the 3 would be your thousands place, right?
Yeah.
So here, this is just actually 2 to the 0. So this is base 10. 10 is your base, and then you're just raising it to an exponent. So here we're doing base 2. So 2 to the 0 is 1. Anything raised to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is what?
4.
Exactly. 4. 2 to the 3 is...
8.
So rather than having a ones place, tens place, hundreds place, thousands place, you have a ones place, a twos place, a fours place, and an eighth place. So now we can count in binary. If you want to assign each of the letters in the alphabet these numbers like this, okay, let's say you want to communicate Z in ones and zeros, right? Well, Z would have 27, right? Or 26, rather. Sorry. Z
Knows all this, doesn't know how many letters in the alphabet.
So if we wanted to communicate 26 in binary, this is going to be your 16s place, this is going to be your 32s place. Well, 26 is bigger than 32, so we can't have anything in the 32s place, right? But we can have something in the 16s place, right? So we're going to have 16 there. Now, how many do we need to get to 26? We need 10 more, right? So to get to 10, you're going to need an 8, and you're going to need a 2. You fill in the rest with zeros, and that means 26 in binary. Because again, pretty much all you're doing is doing 1 times 16, or 10 to the, or 2 to the 4, it's the same thing, plus 1 times 8, plus 1 times 2, add those all up, you get 26 in decimal. So we can count in decimal. All we've got to do now is assign every symbol that we want to be able to use a value, and we can now communicate it in ones and zeros. And when they first invented computers, they went about doing that. They organized all of the symbols that you're pretty much ever going to need to use into something called the ASCII table, which is what I'm passing out right now. If you wanted to communicate the letter A, for example, lowercase a, well, let me teach you how to read this table real quick. The first column here is decimal numbers. The second column that says HX up there is hexadecimal. That's base 16. We'll get to that in a minute. But then the last column that says char is short for character. So pretty much look for the character that you want in the last column. If we want a lowercase a, what decimal number is that associated with?
97.
97, exactly. So if I want to communicate lowercase a to you in binary using the ASCII table, I need to give you the number 97 in binary. Again, we're going to have ones place, twos place, 4, 8, 16, 32, 64, and 128. 128 is too big, right? We're trying to get to 97. So, can't have a 128. 64 fits into 97, doesn't it? So we can put one of those. Can we put a 32? Will that fit in there? Yeah, so 64 plus 32 would be 96, right?
0, 0, 0, 0, 0.
Exactly. So we just need one more. Put it in the ones place. So this string of binary numbers in decimal is 97, which according to ASCII means lowercase a. That's how computers communicate with each other. So information is
32.
always given in bytes. A single one of these digits is known as a bit. You put 8 bits together, you always do 8 bits. 8 bits like this is a byte. So you'll notice that there's 8, 1, 2, 3, 4, 5, 6, 7, 8. 8 bits together is a byte. Information is always given in bytes because it's always given as an ASCII symbol.
So it's always 8.
Yeah, so it'll pretty much look at a string of 8 numbers, figure out what symbol that's supposed to mean, and then it'll look at the next 8 numbers, figure out what symbol that needs to mean, and so on. And again, there are codes for like a space. If you look in number 32 decimal, that's the ASCII code for a space. But yeah, that's pretty much how it works. And so how does a computer store that kind of information now? Like, all right, we've learned that you can communicate in ones and zeros, but how would you store any information or transmit it for that matter? Well, you need to find some way of storing ones and zeros. A really common way of digitally storing information is on a CD, right? Well, not so much nowadays, but CDs used to be a really popular way of storing information. So how does a CD store tons of ones and zeros? Well, if you look at a CD like under a microscope, it's really cool. Pretty much the way a CD works is you've got this circle of plastic and then they put a layer of aluminum foil basically onto it. That way when a computer takes a laser and bounces it off of the aluminum foil, it'll bounce back. But if you punch a tiny little hole in the aluminum foil, the laser will go through and not come back. So the computer has this little laser, it bounces it at a spot on the CD. If the laser comes back, it reads that as a 1. If it doesn't come back because there's a tiny little hole in there, that is called, it considers that a 0. So if you look at a really, really close-up picture, a microscopic picture of a CD, it looks like this. There's tons and tons of microscopic little holes. The hole is associated with a 0. A not hole is considered a 1. So like right here, this is the shortest hole we see, right? It has a length of about 900 nanometers, so that is a single 0. But if 2 zeros were right next to each other, this would just be twice as long, right? Well, this is pretty much exactly twice as long. If I wanted to read this string, it looks like that's a 0, that's a 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0. That's how CDs store binary information. And then there's lots of different ways to do this. You can do this optically by bouncing a laser or by shooting a laser, and if it bounces back, that's a 1. If it doesn't, that's a 0. You can also do it electronically. Computer chips have tons and tons of tiny little capacitors on them. And capacitors are these things that can store a charge. So pretty much it looks at a capacitor. If it has a charge stored on it, it considers that a 1. If it doesn't have a charge on it, it considers that a 0. That's how information is stored by a computer, and then how is it transmitted by a computer? Well, computers can send like radio waves and stuff, right? You guys are familiar with radio. Well, have you guys ever wondered what the difference between AM and FM radio is?
Wavelength.
Oh, I remember him doing that.
Not quite. Pretty much what you need to do is you need to code a bunch of ones and zeros into a radio wave, right? So you have your regular radio wave, you need to change it ever so slightly. If you change it one way, it considers that a 1. If you change it a different way, it considers that a 0. So the two major characteristics of a radio wave are the amplitude and the frequency, right? You can vary the wavelength ever so slightly. So you tune into a certain frequency, which just corresponds with a radio station, and then an AM radio station will change the amplitude of the wave ever so slightly. If they make the amplitude a little bit larger, that considers it a 1. If it makes it a little bit smaller, it considers it a 0. So it's amplitude modification, AM radio. Whereas an FM radio will change the wavelength ever so slightly. A tiny bit longer means 1, a tiny bit shorter means 0. That's frequency modification, FM radio. So you can pretty much code ones and zeros into electromagnetic waves and then send them super fast. Because electromagnetic radiation is the same thing as light. Like, it doesn't matter if it's visible light, infrared lights, radio waves, gamma rays, microwaves, all of those things are electromagnetic radiation. They're all the exact same thing, just with different wavelengths, and they all travel at the speed of light. So you can send messages at the speed of light and just code a bunch of ones and zeros in there, and because it's traveling so fast, you can code tons and tons of ones and zeros in there, and you can transmit a bunch of information like that. So that's pretty much how it works. That's how computers digitally store information. But how would they do like a picture, for example? How do you convert a picture into a bunch of ones and zeros? Well, you guys probably know that if you zoom in on a digital picture really, really close, it's made of a bunch of pixels. Thank you. So we got what looks to be a normal picture right here. If you zoom in really close on the ear, you can see all of the individual pixels there. And so you can code information for each pixel in ones and zeros. Pretty much you code information that says row 1 and then information that says column 1, and all right, they know that you're talking about that pixel. And then as for what color that pixel needs to be, you guys learned in elementary school that you can get any color by mixing the primary colors in different ways, right? The primary colors when you're mixing paints, at least pigments, is red, blue, and yellow, right?
Yeah.
Okay. Because I get confused sometimes because it's different with pigments and light. When you're using light, the 3 primary colors are red, green, and blue. Not yellow, green instead. And so pretty much each pixel on your computer has a tiny, tiny little red light, a teeny, tiny little blue light, and a teeny, tiny little green light. And so you then just send information about how bright the green light needs to be, how bright the red light needs to be, and how bright the blue light needs to be, and that will show up as a different color. So you just say, okay, the pixel in column 1, row 1 needs to be this, or have this much green light, this much red light, this much blue light, and it shows up as that color. You do that for every single pixel, boom, you've got a picture. So how would that work for audio information, for example? Well, you guys have now learned that audio, sound, is just made up of waves, right? And the 2 major characteristics of a wave are the amplitude and the wavelength. And so you say, okay, for this nanosecond, play a sound that has an amplitude of this much and a wavelength of this much, and that'll produce a tiny little sound. And then, okay, next nanosecond, play a sound with these characteristics, and then you do that over and over again, and boom, it plays sound. So if you want to play video, for example, well, you've just got to combine sound with video, and all video is a bunch of pictures happening really fast. Like if you see a new picture every like 0.04 seconds, that means you're seeing pretty much 24 frames, 24 pictures in 1 second, and your eye just sees that as a moving video. So it's just sending you a new picture, like 24 new pictures a second, audio along with that, boom, you've got a video. That's how it works. The first byte says 0, 1, 0. we need to find out what symbol they're trying to communicate to us. So again, you've got all of these different places, the 1's place, 2's place, 4's, 8, 16, 32, 64, and 128. So you've got 64, so you'll do 64, again, 1 times 64 is just 64, and then a 4, so we got a 4, and then a 2, that'd be 70, right?
Oh, so then you go to 70 and
Yeah.
7.
So go to 70 in your ASCII table, and what symbol is that?
F, capital F.
Capital F. So this byte here
Oh, so
means
that's just one whole letter?
that's one letter.
This is making one zero.
That is really hard, right? Well, there's a much faster way to do it.
Yeah, I was gonna
If
say.
rather than converting from binary to decimal, you convert from binary to hexadecimal, which is base 16. So, if you're using base 16, you can break the byte up in, you can break the byte in half. They call half a byte a nibble. That's legitimately what it's called, though. So let's do that for the second number here. So let's break this in half. If you convert to hexadecimal instead of decimal, you can break it in half. If you're doing decimal, you cannot break it in half. It only works if you're doing hexadecimal. But now we're going to have a 1's place, 2's place, 4's place, and 8th place, and then start over, and again you have 1, 2, 4, 8.
Well,
So
When can you do that one, when can you do that one?
if you're doing hexadecimal, base 16, you can break it in
Oh,
half.
got it,
If you're doing decimal, you cannot break it in half.
okay.
But we're going to do hexadecimal. So we're going to translate this string of binary into hexadecimal. So again, hexadecimal just means base 16. Pretty much what we're wanting to do is convert this from 8 numbers into 2 numbers. If you combine every different combination of the 1's and 0's in 4 bits, there's only 16 different combinations you can make, right?
Yes.
So if you just had 16 different symbols, well then you can convert this into a single symbol and this into a single symbol. You just need 16 different symbols to do it. So hexadecimal, the way it works, this is going to be decimal, and this is going to be hexadecimal, or just hex. It starts off the exact same way. 1 in decimal is 1 in hexadecimal. 2 is 2. 3 is 3, and so on. But when you get to 8 and 9, again, you still got 8 and 9. But in hex, we're going to need 16 symbols. And in decimal, you start over, and now you're using 2 symbols. You can't do that in hex. So a 10 in decimal, they call a capital A in hexadecimal. And then 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. I know I said 16, but you don't actually move on to G. The first one is actually just 0 up here. Right? So this number in hexadecimal is just, you've got a 1 in the 2's place, so that's just a 2, right? 2 in hex is still just 2. Here, you've got a 4, a 2, and a 1. So 4 plus 2 plus 1 is 7. 70, so now you've got a nibble that's 7 and a nibble that's 2. Again, we're in hexadecimal here. So looking at your second column on your ASCII table, hexadecimal column, what is hexadecimal 72 as a character?
R, lowercase.
Lowercase r. Does everyone see that?
Yeah.
So that's how you do hexadecimal. So this string is 90 in binary, but it's, again, way easier to do that in hex. So let's
Hey.
convert this to hex. Break it in half.
How do you know when to do hex?
Always.
Yeah, always,
It's honestly, it's easier.
always do hex.
What if there's nine?
That's cool, it Mrs. Hardy made.
I
That'll be a
made this.
huge
Oh,
number.
you made this? But why does it say that?
What?
Why'd you put it to say that? You made
Because this
this.
is a message from her.
Oh, okay.
Well, yeah,
Well,
I
that's
made
really
up a
awesome.
message.
No, you can't look.
How did you do it?
Yeah, the coded message is a message from Mrs. Hardy. Not actually from her, I just made it up.
Literally. Literally.
Okay, so here we broke it in half. We've got an 8 and a 2 is a 10, right? But a 10 in hex, what's a 10 in hex?
A.
A. So that's going to be an A. Here on this side, you've got a 4 and a 1 is a 5. If you look up 5A as a hexadecimal number in your, it's capital Z.
I love this.
No, there it is. Okay.
I know, I think it's fun too.
How'd you get A?
This is 8 plus 2 is 10, right? But we're in hexadecimal, so a 10 in decimal is an A in hexadecimal.
And then from 5A, how'd you get 90 or whatever? How do you find by 90?
Okay, so on your ASCII table, the first column is decimal, the second column is hexadecimal. So look in the second column, try and find 5A. It should be at capital Z. Also known as 90.
Oh, okay, I see.
Okay.
I got it.
So let me do a couple more examples to help you guys with these first 4 problems, right? So again, let's do binary here. We'll do decimal over here, and hex here. So if you have a number in binary, the first digit is going to be your base 2. Binary is base 2, so base 2 to the 0. And then base 2 to the 1, base 2 to the 2, base 2 to the 3. If you want, you can rewrite that as 1, 2, 4, 8, right? When you're doing decimal, it's the exact same thing. The first is your base. Decimal is just base 10. So you have your base to the 0, and then 10 to the 1, 10 to the 2, 10 to the 3, which, if you want, you can rewrite as 1, 10, 100, 1,000. And then when you're in hexadecimal, your first one is 16, base 16 is what hexadecimal means, to the 0, 16
Oh my goodness.
to the 1, which you can just rewrite as 1 and 16. Okay? And so when you fill numbers into here, the way it's going to work is, so the first example is 42 in decimal. I'm not going to do this exact one, but let's say I do 38 in decimal. I'm just going to do 3 times 10 plus 8 times 1. Let me do it this way. Is going to be 38, right? But here, you're going to need some more digits here. Convert 38 to binary. So we can fit a 32 in there, right? So there'll be a 1 right there. We need 6 more. How do we get 6 in binary? 4 and 2. And so all you're doing here is 1 times 32
Do the bottom one?
plus 1 times 4 plus 1 times 2
Oh, I got the. Oh, I get it now. I didn't get it at
is
first.
32 plus 4 is 36 plus 2 is 38. And again, with hex, it's really easy because you're always multiplying by 1. So you don't even really need the 1 times. You can just do 32 plus 4 plus 2. Hexadecimal can get complicated though. Let's say you've got the number 4C in hexadecimal. What does that mean in decimal? Okay, well you're going to do 4 times 16. We're doing the exact same thing, right? Got 4 times 16 plus C. What does C mean in hexadecimal? No. C in hexadecimal is 12. So this C here just means 12. So you're going to do 12 times 1. So you've got 4 times 16 is what? Go ahead and for me. Well, 32 would be 64, right? Okay, so 64 plus 12, 70, 76? So this means 76. The hex to the decimal? Okay, so I'll do an example of a hex to a decimal. Just like on your problem here, you got to do A6. as hex into decimal. We do a different example. I'll do B4, right? So in hexadecimal, this is your ones place and this is your 16s place, right?
Yeah.
So you gotta do whatever this number is times 16 plus 4 times 1. What is this number in hexadecimal? B is 11, right? So you're gonna have 11 times 16 plus 4 times 1. 11 times 16 is 176 plus 4 is 180, right?
Why do you know that? Copyright.
I like the message.
Thank you.
We already.
Yeah.
So with A6, so it's gonna be 10 times, what, 16?
Yeah.
10 times 16 plus 6 times 1.
So 166.
Yep.
We don't have that big of we don't have that big of a number. ASCII table we're gonna
Oh, I see
expand.
what you're saying. I'm sorry. Yes, this is only half of the ASCII table, actually.
Okay.
This is generally referred to as the ASCII table. There is another table this exact same size, which is generally referred to as the extended ASCII table, but the symbols that it's associated with is like the Greek alphabet and stuff that you hardly ever use,
So
so
like pi.
this is the one that's pretty much always.
So we just use X all the time.
Yeah, like, if you're looking at computer code, it's always gonna be in ones and zeros. You can convert those ones and zeros to decimal, but it's a whole lot harder than converting that ones and zeros to hex. If you use hex, your life's gonna be way simpler.
I like that.
That's a hard problem. I don't think I've done an example of decimal to hexadecimal, so. This is 77 in decimal. I want that
Yeah.
in hex.
It's 8 feet.
Yeah.
So, in hex, we've got a ones place
Because 12 is C.
and a
And
16s place,
1.7 plus
right?
12.
Yeah.
16
So
times
how
8.
many
Oh.
times can you put 16 into 77 whole? Yeah. Yeah. Whole. So if you do 77
4.
divided by 16, it's going to give you some number.
4.
Point. Okay, so 4.
So you need the.
So if you put a 4 there, so 4 times 16 is what? That's 64. So to get from 64 to 77, you need 13 more, right? So what's 13 in hex?
My day's complete now. Always wanted to read code. Know how to read code.